Okay, I want to take the generic version of the chain rule that deals with composite functions, which I have over here, derivative f of g of x, okay, which is what we've used up to this point, and I want to apply it to specific functions so that we can think of our regular function-specific rules, just augment it a little bit to work, so we don't have to refer back to this long version of a chain rule over and over. So let's see here. Down here I have the power rule, which is usually, let me rewrite it the way it usually is usually the derivative of x to the n, and that would be n times x to the n minus 1, where x is a variable. Well, I've come over here and I've replaced that x with u. Now u could be a expression or a function similar to the way we use it in the product rule or quotient rule. And if we do that, then something to the n is our f, but the something is our g. So we can think about this u being the g, and if the u is the g, then we would tack on the g prime. Let me change that color a little bit. So we can take all of our function-specific rules and let the function itself be the f, and let the variable in there, the x, be the g. And then we can apply everything as normal. So the natural log of x becomes the natural log of u, and the derivative of that would be 1 over u, but tack on a u prime, okay, similar to the g prime. So let's see how that works and see if it makes our life a little bit easier. Okay. So this is a problem we did the long way, natural log of 5x to the fourth. Well, let's just do it with a function-specific chain rule here. So we're letting u be 5x to the fourth. And remember, this is the same thing as u or g. So when we take the derivative of natural log, we get 1 over that u part, and then times the derivative of that u part. So there'll be a u or a g and a u prime or a g prime. So we will drop this u back in, 5x to the fourth, and derivative of that was 20x cubed. Okay. So basically I took my u and tacked on the derivative of u. Okay. Think of u and g as the same thing here. And I can clean up a little bit. We talked about 20x cubed over 5x squared would give us 4 over x. Okay. Whether you clean it up or not, it's the same derivative. Okay. Another example we've worked was the quantity of 4x cubed minus 5x all to the 8th. Well, before we let this 4x cubed minus 5x be g, now we're just going to call it u. And we're just going to handle that as it's either u or g, whatever you want to call it. But the actual f here is something to the 8th. So derivative is 8 times something to the 7th. The u goes back in there. We'll tack on the u prime. So the u was 4x cubed minus 7x. And then the derivative of that was 12x squared minus 5. Clean up if you like. But we assumed what I highlighted here, 4x cubed minus 5x was g. That relates to the u. So we don't have to list everything out. Okay? Because we know that the power function is the f in this. Another example here is 7 times the quantity of 5 over x squared plus 9x cubed all to the 17th. So once again, this is a power function. Something is being raised to the 17th, so that something inside there must be the u. Okay, or the g if you like. Call it g or u if you like, whichever. But the derivative of this thing, the 7 coefficient stays, the 17 exponent comes out front, and the exponent goes down to 16. So u is going to go inside here, and then on the outside we will have u prime. So u is 5x squared plus 9x cubed, and we got to take the derivative of that to put on the outside. I'm going to rewrite it because I don't like the denominator there. So I can rewrite 5x squared as 5x to the negative 2 plus 9x cubed. So derivative of that would be negative 10x to the negative 3. Negative 2 minus 1 is negative 3 plus 27x squared. If you want to clean that up, you can, but negative 10x to the negative 3 plus 27x squared. So we used the power rule, but instead of having just x in there, we had an expression, so we tacked that on toward the end. So we're implementing the power rule into our traditional function-specific rules. Next, I have the fifth root of 7x cubed minus a natural log of x. Just because of the way that power is there, I'm going to rewrite it. So derivative of the fifth root, let's use some colors here to be distinctive, 7x cubed minus natural log of x, and we'll raise that to the 1/5 power. So in that case, this is another power function that's something to the 1/5. What's being raised to the 1/5? 7x squared minus natural log of x. That'll be our u. So when we take our derivative, we will have from the f part 1/5 something to the negative 4/5. Our u will go in there. And then it'll be times our u prime. So let's see here. U was 7x cubed minus natural log of x. That's the same thing as g. And the derivative of that will be 21x squared minus 1 over x. Okay, like I said, we can clean that up if we like, but that's not my focus right now. Okay. The next one, e to the 5x squared minus square root of x. So it's e to a power. So in general, the derivative of e to the x is e to the x. But now we have a complicated thing up here. So our g or our u is 5x squared minus 5x. But we just said the derivative of e to something is e to that thing. We'll put it up here. And then we will tack on the derivative of it. Okay. So the u that we have is 5x squared minus square root of x. But we need a derivative of that. Once again, I'm going to come down here and rewrite it since we're using a square root here. So 5x squared minus x to the 1/2. That is our f or g if you like to call it that. The derivative of that will be 10x minus 1/2 x to the negative 1/2. So we'll tack that onto the end. 10x minus 1/2 x to the negative 1/2. Not much cleanup you can do there unless you really want to write things as roots, and we'll move them to the bottom. Okay. I think I've got one more before we get crazy here. Natural log of the square root of 5x plus 7. So I need to rewrite this thing, I feel like. It's the natural log, messy. Natural log of, instead of square root, I'm going to write 5x plus 7 to the 1/2. And that's what I want to take the derivative of. So this is a natural log, so I'm going to use that rule. Natural log of x becomes 1 over x. But what I have is something complicated, so I have a u here. So let's see here. This derivative will be 1 over this guy times the derivative of this guy. So there's going to be a u down here and a u prime here. So 1 over 5x plus 7 to the 1/2. Okay, and then times the derivative of that. Now the fun thing about this one is that that is also another chain rule. So the derivative of 5x 5x plus 7 to the 1/2. Okay, let's do a little bit extra color here, because this is our u right now, and we're trying to take the derivative of it. But it looks like there's another chain rule. So we have chain rule inside of chain rule. So this 5x plus 7 is a u for the nested chain rule. So let's see, if we write that out, derivative of this guy would be 1/2 something to the negative 1/2. So there'd be a u in there, and then there'd be a u prime tacked on. So the u of this one is 5x plus 7, and the derivative of that is 5. So in this guy right here, in the nested chain rule, we have a completely different sets of u's. But this guy over here, 1/2 times 5 plus 7 to the negative 1/2 times 5 is the u prime that we've got for the original problem. So let's clean it up just a little bit. It'll be 5/2 5x plus 7 to the negative 1/2. Now the neat thing about that, let me draw a nice box of a different color around it, is that if you take the negative 1/2 power to the bottom, it'll combine with the other negative 1/2. So it cleans up kind of nicely. 5 over 2 times 5x plus 7. If you use something to help you find derivatives, that's probably the way it will write it, because it will take this negative exponent to the bottom and combine it with the other one. But that's a nice, neater answer. But if you don't clean it up, this is where you'll end up. But be careful, because there was a chain rule inside of a chain rule. And I think we've done product rules with product rules inside of them. But then again, everything is meant to just get more complicated and more complicated as we go. Derivatives, there's a limited number of rules, but an unlimited number of ways you can combine functions. So you have to figure out how to decompose them to fit those rules.